All right, we're recording.
All right. Good afternoon, everyone. I'm Sid DeMayo. I'll let everybody else introduce themselves real quick.
I'm Joel DeZona.
I'm Caleb Dalbo.
And for our group presentation, we're going to be discussing load resistance, which is chapter 4 in our textbook, going over structural properties of materials, and diving into some other topics under that genre.
Oh, there it is. All right, so we're going to talk a little bit about the history of load resistance and kind of a basic understanding of various construction materials that are used throughout history. The discovery of the arch, which, as you can see, has been used in years past, also led to the development of the dome, which was another great discovery to be able to build very large spaces indoors. The brittle use of stone and how it became perfected during ancient times. The Industrial Revolution led to great innovation of different architectural styles and really implemented the use of iron. And then today's materials and architecture and how they vary compared to the past are much different considering the technology that we used today.
So that was a little bit about so background history, and so going into specifically the history of beams and its development over time. Kind of a more primitive building in the 16th century up to the middle 19th century. Large wooden timber beams were used for construction of homes and some buildings. But because of the development of steel beams, the need for using wood due to fire risk it's just declined over time, and steel is more, just much easier to manufacture, more economically efficient. So now timber beams are kind of just more used in homes for aesthetic purposes, for just kind of that vintage look or whatever. So the I-beam, which is kind of the most famous steel beam, was first developed in 1849 by a engineer, Alphonse Halbau. It was first put into use, however, in 1889, so 40 years later, in Chicago, the Rand McNally building. So that was the first all steel frame skyscraper. It still exists today. But an English engineer named Henry Gray perfected the I-beam. So in the Rand McNally building, it was used, but Henry Gray kind of perfected its use. So early I-beams could only hold 20 stories in terms of their load capacity, but Gray, he developed this new rolling method. So the I-beams could be strengthened so they could be made into bigger sizes and hold larger load. So, and funnily enough, the first building that used Gray's method was a factory to develop more and manufacture more I-beams. So there's other beam types, the rectangular beam, which is just a concrete frame or just concrete rectangle beam. So nothing too special there, but that was developed just for, maybe like a parking garage type structure. Composite beam, the first testing began in Canada in 1922. So it's been developed for almost 100 years now, and kind of used for in the same situations as precast concrete beams, which interestingly enough, ancient Roman architecture utilized precast concrete to make their buildings back in those times. And then this is a graphic of the Rand McNally building, a vintage photo. Again, that was the first all steel framed building that used I-beams.
All right, so we'll talk about the history of arches. And so like it says, arches appeared that we know of as early as the second millennium BC, but I found some stuff online that says that it was may even be more like 4000 BC, so maybe even older than that. And they were used rarely, mainly for underground structures like tunnels and stuff like that, up until the Romans, and the Romans were famous for being able to actually move those underground structures that utilized arches to above ground and really made them look pretty and mastered the craft of it. So as of now, there's 17 main types of arches, and they range from all different kinds of shapes, but they're all basic. I mean, it's just an arch. But so this is just this one in this picture is called a regular semicircle, but there's even parabolic or elliptical arches. And then, like it was said earlier in the presentation, once they mastered arches, then that led to the discovery and mastery of domes, which really opened the door for new building techniques. And then just going through a quick like anatomy of the arch, you got those two vertical supports that all the weight ultimately sits on. And then the keystone is the most essential part of an arch. That's the center stone that really holds everything together. And then I don't know what that word is, but those are just like the other supporting stones. And then so the about some more about arches is that the arch is unique in that it utilizes purely just compression for load resistance, which means that like for most types of construction, there's compression and tension, but for arches, everything in the whole thing is utilizing compression, which means that the arch can be built from materials that are strong in just compression and like not worry about if they're strong or weak in tensile strength. So they can be built with stone or non-reinforced concrete. Like you can see here, like the top left picture is a picture of a Roman aqueduct, and then the bottom left is the Colosseum, and then that one in the middle is the Gateway Arch in St. Louis. But like I said before, it's really the arch is unique because everything is held in place by its own weight of everything that's there. So there's nothing else. There's no screws or anything holding it into place. It's just the weight and friction of what's there. So they're a little bit difficult to construct, but it's usually they just build like a wooden frame underneath it and then set everything in place. And then once everything's in place, then you just take that wooden frame out and then hopefully everything stays, but that's not the case every time. But they like I said, the Romans mastered it and it's been used quite a bit ever since in regular arches and now in domes.
All right, so we're going to talk a little bit about the yield stress and ultimate strength. And this can vary depending on the structure that you're testing or the situation. Like, so for example, if an I-beam were to be resting on two supports on the exterior of a building, the middle part would only be actually uh, would actually, the load would only cause a deformation in the middle and not necessarily the outside parts of an I-beam. But the relationship of stress and strain is proportional. Generally speaking, they do occur at the same time when weight is placed on a structure that is, for example, load bearing. And this diagram kind of shows you where the elastic region versus the plastic region, and the yield strength and the ultimate tensile strength, where the building forms can actually be measured against. And then so here we have a picture of tensile strength where load versus compression. So in this picture down below, oh shoot. This picture down below here on the bottom right-hand corner, the beam on the top that is curved is the beam that is in compression, while the beam on the bottom half is in tension. And the compression is from gravity, and being that the weight is held by that lower beam, therefore it is in tension, and it is measured by the ability of the material to resist being pulled apart to be able to actually determine the strength, the tensile strength.
Yeah, so Joel just kind of gave a good segue into compressive failures. And so compression is the capacity of a material or structure to withstand loads tending to reduce size. So basically, when there's either one force pushing on something in one direction and it can't move that direction, or if there's two forces pushing inward on the same object. So like you see in that picture, in compression, the part that actually fails, the material will go like outwards. And with compressive failures, there many of them include fractures or irreversible deformities, like you see in that picture. And one of the unique things about compressive failures, as opposed to tension failures, is that there's no warning signs, and everything usually happens pretty quick. And then that leads into tensile failure, which is just the opposite. So as you can see in that diagram, it's just when there's one force pulling apart or pulling the opposite direction, or there's two forces pulling apart from each other. And so it's tension, and it's when something's being pulled from both ends or from one end with the other end not being able to move. And you can think of this as like stretching with like rubber bands and stuff like that. And so as you can see, in a ductile material, which means that it's like malleable, like it can be like reformed without losing its integrity for the most part. There'll be that when a failure occurs, it's usually pretty gradual. So like you can see in those pictures, the deformities. So like when you start pulling it apart, it gets thinner at the middle, as opposed to with compressive failure where the middle gets bigger because the material is being pushed out. So that's when that material in the middle at the failure point gets smaller. That's known as necking. And materials that are like that are steel and aluminum. But tensile failures can occur in brittle material too. But the only difference is with that, there's hardly any signs of failure. And when it does fail, it's usually pretty quick. So you think of that as like a brick or like concrete and stuff like that, where if you try and pull on it, and then like it'll break in the middle, but it's not going to show any necking like you see in those pictures.
So that leads kind of into another type of failure, a different type than compression and tensile failures is buckling. And just off the bat, buckling and bending are kind of similar, except buckling, by definition, the load and the force is being applied to the top of the member instead of to the perpendicular. So if for example, if you look at this image of, think of crushing a can. If you try to crush it from the top down, takes a lot more force to do so than if you just kind of touched it. You can even put a dent just by touching an aluminum can on the side, and that would be like bending. But buckling is when you would crush it from the top down. So yeah, it occurs to long and slender members, subject to that axial compressive stress. Steel columns are more prone to buckling than concrete columns just because of the nature of the manufacturing. They're more slender. And when you have, a long column that has a smaller cross-sectional length, that just makes it a lot more prone to buckling. So yeah, again, that visual gives you just an idea of buckling and kind of what that means. And you can also think of, if you just take some sort of something that can bend, and you try to push it like a stick, when you try to push it at, top down like this, it's gonna bend outward. So yeah. So yeah, here, kind of building on that, the way to reduce the risk of buckling, especially on like stud framing, so you can either increase the thickness of the member if it's too, slender, but economically that is just not feasible for most cases. So in the visual, you can see the stud blocking where it's basically, you just brace those stud frames, the vertical stud frames. So that's just to prevent those vertical wood studs from buckling. In this case, obviously the photo that was taken there, the stud blocking was necessary, but building code determines in which situations stud blocking is necessary. So you'll find that out just by looking at the building code for certain projects.
So now we're going to talk. We have a few famous or like noteworthy structural failures, and the first one is the Great Molasses Flood of 1919, which occurred in Boston. And what happened was it was a 50-foot tall and 90-foot in diameter, basically like a silo to store liquids, and it held 2.5 million gallons of liquid. And what they put in it was industrial grade molasses, which was meant to be distilled for alcohol to use in making explosives for World War One. But I'll talk about it in a bit. But basically, the construction was super rushed, and like they didn't take the necessary precautions and stuff due to prohibition, and that technically they weren't supposed to have all this molasses because it was used to make alcohol. But so yeah, as you can see, there's poor construction and testing. But so it failed due to a combination of multiple things. And first of all, the tank was constructed poorly, and there wasn't sufficient testing from the beginning. So it wasn't. I mean, from the beginning, it was kind of like doomed. And the engineer had no prior experience since like before he took this job. So that just like another thing that seemed like it was bound to go wrong, and it actually did here. So like I said, that they were in a race against the ratification of prohibition. But structurally, the things that were wrong with it, so the width of the steel walls were only about half as thick as they should have been, which we have like determined since then, like engineers just in the past 20 years or so determined how thick the walls actually should have been, and they were only about half as thick as that. But and then on top of that, the design that they used for the rivets in the tank were flawed, and then there were also like visible cracks all over the thing whenever they would. So like they did testing with it before they actually put molasses in it, because molasses is 1.4 times like as dense as water. But so they did the testing with water, which again isn't sufficient because there's a pretty big gap in the density and the weight. So, but they did that with water, and then I mean, anytime they filled it, there was like cracks all over the place and leaking. But like they ended up just going with it and filling it up. Like it says in that picture, they had 23 or 2.3 million gallons of molasses in it, and uh, like the cracks were so bad that they they got to the point where they just painted the whole thing brown, so that like all the molasses that was leaking out would just blend in a little bit more. And there was like they actually had like neighborhood kids, like their parents would send them to this molasses tank because they knew that it leaked so bad. So they would send them with mason jars to catch molasses out of the cracks, so they didn't have to go to the store and buy it. But yeah, so anytime they filled it, it would produce loud groaning noises and cracks and other warning signs, but they just ignored it every time. But I mean, it really comes down to it was just like a bunch of like ignorance on basically everyone's part that was involved in this. Like it, I mean, it seems kind of funny like now because you look at it and you don't hear about this kind of stuff, but when it happened, it actually killed 21 people and injured at least 150 after they got all the counts and everything was settled. So I mean, it seems a little bit comedic to us, but I mean, there's people that lost their lives because there's 21 people that lost their lives just because this engineer didn't know what he was doing and because the company was in a rush. But when it actually did burst, it was said to produce a 25-foot wave moving at about 35 miles an hour. So nowhere way too fast to be able to outrun it. So there wasn't really much options. And the nearby buildings were completely swept off of their foundations. And there were multiple blocks where there was like 2 or 3 feet deep of molasses just sitting. And uh, finally, it's uh, people that live around the area or that like are around that area today will have actually claimed that on like super hot days you can still smell the molasses from like seeping up from like the concrete or just like where all the molasses was. But like it says there, oh, you should go back, Joel.
Sorry about that.
Like it says there that like the official wording for what the failure was a cylinder stress fracture due to poor design and construction. So, I mean, I don't know. I think it just goes to show that, like, while it might not seem like a big deal, just because these people were in a hurry and it was designed poorly and constructed poorly, 21 people lost their lives and at least 150 were injured enough that it was noteworthy. So, I mean, it just shows how important this field really is. And especially when you get into these bigger buildings, like, you have to take the precautions and make sure that this stuff doesn't happen.
All right, so this is a picture of the Tacoma Washington Bridge that failed due to high winds. It was built in 1940, and then just 4 months after opening, there was a storm that came through, and the bridge was fluttering dangerously enough that it actually destroyed it. Um, Part of that reason was because the bridge wasn't an open deck, it was solid on both sides. And as the wind caught it, it just started to flutter very bad. And the picture here with this man standing on the bridge looking back is from a trap driver that was midway through on the bridge as it was fluttering in the air, and he is looking back as he escaped, but it was a scary time. It was actually caught on film as well. If you look up this video, the Tacoma Washington Bridge structural failure, you'll be able to watch the video that they took back in 1940 and actually see uh, how the bridge was reacting to these high mile-an-hour winds. And so this is actually the bridge as it failed. It's an example of elementary force resonance, but it was due to the fluttering of the bridge and the structural instability that the designers didn't predict. So it was by far a learning experience, and it definitely increased the research of future aerodynamics in bridge construction, as well as the elastic properties of materials that are used on different bridges and even buildings that sway in the wind.
Yep. So our last example for a structural failure is probably one that people have heard of or remember. Back in 2010, the Hubert H. Humphrey Metrodome collapsed due to the winter storm in Minneapolis. The Vikings, Minnesota Vikings, NFL team's home stadium, collapsed due to a huge snowfall the night before, early in the morning, due to just huge snow load and just a huge amount of force of compression on the dome. So yeah, the host stadium for the Vikings and other sporting teams in Minneapolis was the dome. So the winter storm, 17 inches of snow caused the collapse of the inflated dome. So we talked about earlier how the development of arches led to the dome. So this kind of ties in with that. But so the snow, just that all that weight on it caused 3 roof panels to tear. And you can see there's video of it happening in real time of just the tear in the roof and just the snow coming straight through. So, and then it led to the total collapse after the initial tear. So some of the reasons for why it happened, it was opened in 1982. So, and this collapse happened in 2010. So that's, 28 years later. And they had some instances before where they had to do repairs and work on it, but it was so old and hadn't been truly repaired correctly in a long time. So their like system for dealing with snow, obviously in Minnesota they get a bunch of it. They had a warm air heating system for the roof just to melt it off, and that was kind of their fail-safe, way of dealing with the snow load. And it was just way too much snow for it to handle. So too much compressive force on the roof and supporting members, and those 3 initial roof panels tore and the snow came in and the entire dome collapsed due to that compressive force. And that graphic on the left kind of was an in-depth look at some of the reasons, and it kind of gives evidence of just the whole how that whole situation progressed. And so yeah, that was that Metrodome collapse due to compressive failure.
So here's a quick summary of what we kind of discussed. The history, I mean, it provided a lot of benefit in furthering research and development of the load resistance and the properties of the materials that are used to construct buildings, bridges, and so forth. and how the strength of the materials truly impacts the architectural form, whereas the arch is specifically a compressive form of architecture. So you're not going to be able to use a something that's resistant to tension, but it must be resistant to compression. And then lastly, just the importance of structural safety and how it all ties in to making sure there's a safety of life and the structure itself, because we all know it's not free. It costs money. So, but yeah, that is our summary. Quick recap of chapter 4. This is team 2 for load resistance and the structural properties of materials.